Good day, everyone. My name is Jim Barton, and I'm a field engineer with Solo.io. In this session, we're going to address what was arguably the most pervasive and flammable cybersecurity attack in several years. This was a latent security risk that raced from zero to a raging inferno in the span of about 24 hours last December. In this talk, we'll provide some background on the nature of the attack itself. We'll review some strategies for addressing the threat and review both their timeliness and effectiveness. And then we'll conclude with a demonstration of one of these approaches. In late November 2021, the Alibaba Cloud Security team reported a zero-day remote code execution exploit that targeted the wildly popular Log4j logging framework. If you've ever written any serious Java code, then you have almost certainly used Log4j. I've used it myself for many years. Well, by early December, this exploit had been weaponized and deployed widely across the internet. Shortly after that, articles began screaming things like, "The internet's on fire." A number of systems from prominent tech organizations were compromised, and emergency response teams from around the world scrambled to respond. This was a really serious issue, and that's why the CVE for the Log4Shell vulnerability was given a criticality score of 10 out of 10. I thought some of the analogies that were published were pretty entertaining. Here's one from a security engineer at Cardinal Health. How I explained Log4j to my mother. Imagine there's a specific kind of bolt used in most of the cars and car parts in the world, and they just said that the bolt needs to be replaced. And then Glenn Thorpe from Rapid7 added this, and the presence of that bolt allows anyone just to take over the car. And then there was this one. Imagine they suddenly discovered Scotch tape spontaneously explodes. You throw out your Scotch tape rolls, then you realize you have tape already deployed everywhere. And this analogy highlights one of the most insidious characteristics of this vulnerability. You might assume that you can simply scan your own systems and look for direct use of a vulnerable version of Log4j. But there's much more to it than that. Not only does direct use of Log4j put you at risk, but any system that depends on a library that uses Log4j could also be exploited. In other words, you not only have to worry about the software you produce directly. With this exploit, you have to worry about your entire software supply chain. And this is a massive undertaking, especially for complex systems. So let's begin our exploration by answering a foundational question. How does a Log4Shell attack work? This diagram from the Swiss government's computer emergency response team illustrates the anatomy of an attack quite nicely. The key to the attack is that a special string is passed to an application via some common mechanism, maybe a request header, maybe a parameter on a request path, or via a posted message payload. And that string conforms to a specific syntax that Log4j interprets as a request for a lookup substitution. Now, most of the time, those substitutions are completely harmless, even helpful. For example, Log4j supports a time lookup. So you add a message to your log saying that you want the time to be displayed in a particular format, and Log4j will replace your time request with the actual time that the message was logged. But what happens in a Log4Shell attack is that a different type of substitution is requested. Most commonly, the attacker requests a JNDI substitution, although other protocols like RMI have been exploited as well. And when an unpatched version of Log4j sees the JNDI substitution string in a log message, it interprets that as a request to look up a Java object on a remote server. Now, if that server is controlled by an attacker, then it can serve up malicious Java classes that will be executed by the application server. When that happens, the attacker can potentially exfiltrate sensitive data from the application or just generally create a lot of mischief on the compromised system. So in short, if number one, the attacker passes a malicious string through a common web application parameter, number two, if your Java application logs that string or passes it to a Java library that logs the string, and number three, if your Log4j instance interprets that malicious string and executes a remote request, say to a JNDI server, then your application is dangerously compromised. So let's turn our attention to some remediation strategies for this vulnerability. We want to answer two questions here. First, if the internet's on fire, how do we douse the flames? How do we fix the immediate problem? And second, And equally importantly, how can we prevent fires like this in the future? Because this is not the first attack of its kind, and it certainly won't be the last. SQL injection attacks have been around for almost a quarter century now, and they operate on exactly the same principle as Log4Shell attacks. A malicious string is processed through a valid input mechanism, and it causes an unintended execution sequence in the application. JavaScript injection attacks follow this pattern too. And now, even more recently, the Spring4Shell set of vulnerabilities that were widely reported in March of this year, they operate on precisely the same principle. So how do we stop attacks like Log4Shell and its relatives? How do we prevent them from going forward? Or at the very least, how can we lay a foundation that will make them easier to stop next time? Well, at a fundamental level, we have three opportunities to respond to these attacks. One, we can intercept the malicious request when it enters our system. That leads us to technologies like web application firewall that we'll discuss in more detail shortly. Number two, we can interrupt the processing of the malicious request inside our application servers. We might do that by patching Log4j or perhaps reconfiguring it to disallow remote lookups. And third and finally, we can block the outbound requests that attempt to reach the attacker's server. So pretty simple, right? We either catch it at the ingress point, we interrupt its internal processing, or we stop it at the egress point. Those are our options. So let's begin by considering the middle option of blocking the processing of the malicious request internally. I start here because this is where I've observed a lot of the focus within enterprises. And it involves activities like asking developers to inventory their applications and identify vulnerabilities, or perhaps automating that activity using a variety of scanning technologies. Then once vulnerable systems are identified, there's a process for applying the fixes. That might include upgrading to newer Log4j libraries, or perhaps reconfiguring the version of Log4j you're already using, maybe even modifying application code to avoid certain dangerous features. And then, of course, those changes need to be functionally tested, perhaps penetration tested, regression tested, and then ultimately deployed. I think we can agree that these can be fairly time-consuming and even labor-intensive endeavors. Now, don't get me wrong. These are important activities, critical, and they need to be carried out. But if you need rapid response to a zero-day exploit like Log4Shell, it's likely not the most efficient approach. So let's turn our attention now to approaches for blocking the outbound requests from the application to the attacker's server. As you recall, a Log4j attack depends on Log4j interpreting a malicious input string as a request to access a remote server. If we can apply policy at the network egress point, then we can potentially stop these attacks without modifying the underlying systems. So this is an approach that could be both effective and efficient, but the challenge is that many organizations do not have a great mechanism for applying policy like this at the egress point of the application network. It's more common to be able to apply policy like this at the ingress point, especially with technologies like API gateways. But there are emerging techniques for establishing policy like this. One of them is through service mesh technologies like Istio, especially when combined with a management plane like Glue Mesh. Istio makes it really easy to assume a zero trust security posture when it comes to network egress. This makes it a really great vehicle for blocking outbound malicious requests. So how do we accomplish this with something like Glue Mesh and Istio? Well, if you're already a mesh user, it's actually pretty simple conceptually. It's just a two-step process. Step one is foundational, to establish a zero trust posture for network egress. Specifically, you'll establish an outbound traffic policy called registry only, which means that only explicitly declared external services can be accessed by services in the mesh. Step two is to use the APIs that Glue Mesh provides to declare what external service dependencies are acceptable. You do this by establishing explicit destination objects that lay out what external services can be reached, and then link the originating service with those destinations by creating a service dependency object. And that's it. Then when a malicious inbound request occurs, the resulting outbound request that is triggered will be directed to a black hole cluster rather than to the attacker's server. So by applying a simple policy and without changing a single line of application code, you can protect all the services within your application network. Now, in the interest of time, we won't dive any deeper into this particular approach, but if you're interested in learning more, let me refer you to the blog from my colleague, Will McKinley, that's linked on this slide. It delves into the details and presents a complete working example that you can test out in your own environment. So far we've discussed two approaches to counteracting Log4Shell attacks. Number one was to block processing of the requests internally, which we said could be effective, but might not be the most efficient approach when responding to a zero-day vulnerability. Number two was to block outbound requests to the attacker server, which could be both effective and efficient if you have the infrastructure like GlueMesh and Istio in place to apply policy at the network egress point. Finally, let's discuss a third approach, which is to block requests at the ingress point by leveraging the Glue Gateway platform. Specifically, we'll look at its web application firewall facility for applying mod security rules directly on board the Envoy gateway. Now, there are certainly multiple WAF providers that are available to users, but we like Glue Gateway because it applies your policy directly at the Envoy gateway point. There are no extra hops required to access an external WAF facility. But first, let's address the more basic question. What is WAF? So web application firewalls offer a standard mechanism to inspect incoming requests and apply a suite of mod security rules to ensure that there's no malicious content. It can be used to block many kinds of threats, attacks like SQL injection and JavaScript injection and the newer Log4Shell attacks, plus requests that come from blacklisted IP address changes and much more. In fact, the OWASP organization offers a curated set of popular mod security rules called the core rule set that you can activate directly within Glue Gateway. And with both the Glue Edge and Glue Mesh Gateway platforms, you can front an entire suite of applications using these rules without touching one line of code in the underlying applications. That's the beauty of being able to apply policy at a single ingress point. So we believe that Glue products provide a killer capability to block inbound malicious requests in a way that is both effective and efficient. If you'd like to explore this technique in more detail with a working example, then check out the blog that I've linked on this slide. But rather than just tell you about using WAF with Glue products, we'd much rather show it to you. We'll do this by demonstrating how to use Glue Gateway to apply a mod security rule that blocks some common Log4Shell attack vectors. And this technique works equally as well in the context of an Istio-based service mesh or in a standalone edge gateway. The mod security rules are absolutely identical. So what we have today is a basic K3D cluster running the 2.07 version of Glue Gateway. And let's switch over to this blog here that I mentioned just a moment ago, and we'll walk through this example. So let's begin by talking just a bit about what we already have configured. First, we have an application workload, the HTTP bin service. You may have used it before yourself. There's a public website available at httpbin.org where you can test various types of HTTP calls to help you understand and even debug your own services. Second, we have configured a couple of Glue Mesh CRDs in our Kubernetes cluster, just a basic K3D cluster. We've configured a virtual gateway that basically defines a listener to the outside world, and then a simple routing policy that directs incoming traffic to the HTTP bin service that we have already installed in the cluster. It's a pretty simple configuration, and I refer you to this blog post if you'd like more details or if you'd like to work through the example on your own. So now that we have this basic configuration in place, we can test our service endpoint and discover that there's a potential security problem here. So if you take a look at the blog here and we copy this curl command, you can see what's happening is we're passing in a malicious, potentially malicious Log4Shell substitution command that targets JNDI, actually sending requests out to this evil.com server. And if we test this curl command, you can see that in fact it works. It works, as expected. It actually passes this this malicious string through the user agent header. Now, if the problem is, if this HTTP bin system, this target system, were using Log4j, then we would have a real security problem here, right? Because it potentially, let's say, logs this user agent content out when the request is received, which would trigger the remote request, and we'd have a problem on our hands. So what can we do to address this this particular vulnerability? So what we're going to do is we're going to take a look at a simple mod security rule that thwarts one of the early attack vectors that was identified for Log4Shell. So as you can see here, a mod security rule is a very simple it's a very simple sort of structure. It basically has there's a predicate that defines what objects do we want to scan for this issue. There's then a matching pattern that says what do we want to match on, and then there's an action phase that says what do we want to do about it if this predicate matches. So you can see what we're doing here with this rule is we're checking all kinds of input parameters to an HTTP request. For example, things like the arguments, cookies, request body, request headers. We're basically scanning for scanning all of these particular entities within the HTTP request for this pattern. And so this pattern is a regular expression that looks for certain strings, for example, that begin with this character sequence and then either JNDI or RMI or one of the other protocols that's potentially being exploited here. And then if we match that pattern, we want to take this action, which is to say we want to deny this request with a 403 status and put something out into the logs. So that's it. That's a simple rule that we can put together pretty quickly. There's also lots of external resources that talk about other rules that might be useful in this context as well. And so what we're going to do is we're going to take that rule, and you can see the rule right here, and we're going to create a Kubernetes custom resource called a WAF policy. And that WAF policy is going to say, hey, I want to apply this to all of the routing rules that have this label WAF equal true, and this is the rule that I want to apply. So basically, with one simple configuration change, we can apply this policy across a whole range of applications, or potentially all of the applications that live behind a certain gateway. So just to show you what that routing rule that we've already put in place looks like, we can take a look inside our cluster. We can see the HTTP bin route table here, and this route table simply takes the requests that come in. It's a very simple routing rule, basically any host, any request path, and we're going to route that to this HTTP bin application. And we're also, you can see right here, we're going to apply any policies that have this label of WAF equal true. And so you can see here, we've specified that label in our WAF policy. So what's going to happen when we specify this, it's going to dynamically apply this policy to the route, and we'll see the results happen immediately. So let's do that. Let's go in here and we will apply this policy that we just looked at that contains the mod security rule. So there we go. We've applied that. Now, if we go back and we try this same attack, quote unquote, that we issued earlier, what you're going to see is, well, that mod security rule has been triggered, and the policy that we specified has caused this request to be rejected. And you can see a little explanatory message here. This is a Log4Shell malicious payload. Okay, so that's working exactly as we expect. Now, there are some other attacks we can simulate here as well. For example, This one shows what happens if we attack through the request argument. So you can see here arg1 in the request path has this same potentially malicious string that we might log out using log4j. So now if we copy that and paste, you can see we get back exactly the same kind of message that this request has been rejected. Finally, we'll show you one other example here, and that'll be the end of the demonstration. Well, what about if this is posted as part of a message payload? So here you can see we're doing a post request, and we are passing this in as an argument as part of the request payload. And similarly, if we issue that command, you can see it's also being forbidden. And so all of these various attack vectors for Log4Shell we can very quickly be able to reject those. Okay. So just a simple demonstration. Again, I refer you to this blog post if you'd like to explore this in more detail. All right, so let's switch back to our slides here for just a moment. And so to wrap up for this session today, we dug into the Log4Shell exploit. We understood a bit about how it operates and why it's such a dangerous problem. We argued that not only does this particular attack present a problem, but indeed it is just another in a long line of similar kinds of attacks. And we not only need to put out the immediate fire, we also need a policy-based foundation that is external to the services that we protect. Why do we need this? So we can rapidly respond to future vulnerabilities that are inevitably going to follow these same patterns. We also discussed how glue products can be used to block this attack at both the ingress and egress points of your application network. And finally, we demonstrated with a real-life example how glue products can be the foundation for effectively and efficiently responding not only to this threat, but also many others like it. So, really thank you for your time. Thank you for listening today. I hope you found this session helpful. Now let's turn and see what questions you have.